Okay. So hello everybody. Today we'll be talking about counting and just some problems related to counting. So I'm sure many of you have a basic idea about what counting looks like, at least in the context of competitive programming. So, for example, um, if you're trying to, some of the most basic counting principles, let's say, would be if I have A ways to choose a certain object and B ways to choose another object, then to choose pairs of these objects will require A times B ways. That's uh, how you multiply when you have independent choice. And let's say I have A different choices of the first kind and B different choices of the second kind. And they're sort of unique in the sense that it can't be the case that I select one from A and one from B. Then that's like A plus B because it just adds up, right? I just have more options to choose from. So these are sort of the two different very basic ways to count. And then they, of course, lead to much more interesting setups. Some common things are, for example, imagine that I have n objects, um, let's say labeled as well, so I can distinguish between them. Let's say 1 to n, and I just want to reorder them in many ways. So, as I'm sure many of you know, the number of ways to do that is n factorial. Then there's also a very standard thing where we have n objects again. Let's also assume labeled. There are other versions to this. And let's say this time I'm trying to select k of them, where k is 0 less than or equal to k less than or equal to n. Of course, outside of that, it does not make much sense. This has n choose k ways, and this is often called the binomial coefficient. And of course, the reason that it's called a binomial coefficient is because it shows up in the expansion of 1 plus x to the n. So the coefficient of x to the k in this is in fact n choose k. But maybe this part is not so important for us. Next, there's also multinomial coefficients, but that is probably outside the scope of this lecture for now. Um, this is also expressible in terms of factorials as this. It's just n factorial by k factorial times uh, this. This also leads to like the Pascal triangle, which is basically like writing 1 choose 1 here, and then you can write actually technically we'll have 0 choose 0 here, then we have 1 choose 0 and 1 choose 1, then we have 2 choose 0, 2 choose 1, 2 choose 2, and so on. So this is the Pascal triangle, and what is true is that the sum of two consecutive elements sort of is also in the triangle in that way, so it sort of adds up. These properties, you can also look at it as having something like n minus 1 choose k plus n minus 1 choose k minus 1 equaling n choose k. And the proof for this is simple using the addition principle. So if you have n objects and you're trying to choose k of them, there are fundamentally two options for any given element. So let's say we fix the nth element. There are two cases. The first case is we take that element. In that case, we've chosen one object, so we need to choose k minus 1 more, and we have n minus 1 elements left. So that's where this term is coming from. This is case 1 of choosing n. And then this is coming from case 2 where we don't choose n. So we still need to choose k elements, but now we have n minus 1. So you could also see this as a DP. And as such, this can also be implemented in n square very often. But of course, given the existence of this formula, we can in fact compute factorials and then answer n choose k queries in online time with linear pre-processing even. So this is all very good. I'll explain again in detail how to do factorials, etc. later. Um, then another thing, um, I think this is pretty much it at the basic level. I think we can just discuss how to calculate some of these. So for example, if I have to compute n factorial, that's easy to do in linear time. I can just multiply all the numbers from 1 to n, and that takes linear amount of time. I could also choose if I want to compute many factorials, I could also, let's say I want to have all of these, then I can also do this in linear time. Of course, modulo something, because these numbers grow large very fast. So it's very likely that you're going to be asked to compute this modulo some prime, usually 10 to the power 9 plus 7, or maybe it's 998244353. Maybe I messed up the second one, but something like that. And this can be done again in linear time. I already discussed an n square approach to computing binomial coefficients, but we can actually speed that up quite a bit. Of course, we cannot store all of these because the number of binomial coefficients is still quadratic, so we cannot hope to store all of them individually, but we can find a very cheap workaround where we can still answer in O of one time, but we don't necessarily store all the possible answers. And the way to do that is simple. We compute this 1 factorial all the way to n factorial, and then we compute what is an inverse for all of these. So we also store these numbers modulo that prime, of course. We can take inverses because the prime is large enough to ensure that the two are relatively prime. That's the only case when we can take inverses. So we can now store all of the inverses as well in O of n time by simply multiplying with 1 by I each time. And then we have all of this computed. And then when we want to find the binomial coefficient n choose k, then that can simply be done because we already have n factorial, and then we have 1 by k factorial, and we also have 1 by n minus k factorial. So we have all three of these values pre-computed, and so we simply need to multiply them, which takes order 1 time. A bit more about inverses because I think that could also use some discussion. To compute inverses, one of the simplest things that we can do is there are, well, two ways actually. One is by using a theorem called Fermat's little theorem, which states that usually this only works when the modulo is a prime. So that's one approach. It works by uh, relying on this modulo p. Here a is of course an integer relatively prime to p, and p is just some prime. Usually it's 10 to the power 9 plus 7 and the other number, like I said above. And this is something that's true, and because now we can compute this by using binary exponentiation in log p time, order log p time, we can answer this quickly. Then there's also the another way to do it is by using the extended Euclidean algorithm, wherein we have a and p, and so we find numbers x, y such that ax plus py is equal to 1. This is simply the extended Euclidean algorithm. You can look this up mm, on Codeforces logs, etc. It's there everywhere. And reading this mod p tells us ax is congruent to 1 mod p. And so, in fact, this number x that we obtain is actually already an inverse for a modulo p. So x is just 1 over a modulo p. That's a second way. And then I like to discuss a third way. So, for example, all of these are very good when you only want to compute one singular inverse. Both of these approaches are quite good. But if you wanted to compute inverses for multiple things, for example, if you were trying to do all factorials and all inverse factorials, then you would need all of these values. You would need 1 by 1, you would need 1 by 2, and all the way till 1 by n. And there is a way to get all of these in linear time, which is quite good. So we can obtain 1 by n, 1 by 2, all the way till 1 by n in order n time. So, well, of course, it's not independent of p, but um, the point is p will only contribute as much as the machine architecture itself would. So we can just ignore the cost that p has. This can basically save you a log factor in the pre-computation. And the way to do this is a little trickier. I'll just explain it. So the inverse of 1, I'm going to call it, let's say, I of 1. So I of 1, we all know that's just 1. And now let's say that we're trying to compute I of x. So we start by actually writing p as p by x times x plus p percentage x, or p mod x. And the crucial property that holds true here is that this number is in fact less than x. Using this, if we now want to reverse x, all we need to do is look at this equation mod p, which tells us that p by x times x is congruent to negative p mod x modulo p. So this is a congruence that holds true. And we can now move x here and move x there and move p mod x here. And that tells us that this is p by x. By the way, note of course that p by x is in fact the floor of p divided by x. So we have p by x times 1 by p percentage x. So this actually I can write off as I of p percentage x times -1, that's just this negative sign, and this is congruent to 1 by x, or I of x mod p. In other words, we've shown this formula that I of x is congruent to p by x times negative I of p mod x mod p. And the reason this is so useful is because this value is just all about dividing two numbers, and that takes order one time. This operation, well, the negative sign is also just known to us. To get I of p mod x, that is simple because this is less than x, and so we've already computed it, because when we were doing our linear pass, we already had all previous values, and so we just know this value, and because we know that value, we can compute I of x by simply multiplying this using the -1 and this other number, which is again completely order one time. So we can compute I of x for every x in increasing order of x in O of one time. And so we can compute I of 1, I of 2, all the way till I of n in order n time. And this can be quite useful again when you're trying to compute many factorials, and so that you can maybe compute binomial coefficients, and you can do all of this in linear time by using this combined with the previous idea of simply getting prefix products, etc. Any questions so far? Okay. So with that, I think that's all for the theory really. Now it's just all about realizing what you're counting, where you're counting it. So I'll just discuss these problems. I hope you all had time to try them. I'll send the link of the first problem in chat again, just so that some of you did not, in fact, read it. You may do so now. So I'll briefly define the problem. I'll attach a screenshot. So for a binary string v, we've defined the score of v as this strange number, which is a certain function f that takes in two indices and tells us this quantity multiplied with so it's sort of like, just you have this we can just assume that v has length n, so I'll do that for convenience. And now all we want to do is cut this into two parts such that the f value of 1 to I multiplied with the f value of I plus 1 to n is as large as possible. So we want to maximize this. But that's not all. Now we are also going to be asked queries, and the queries will be about flipping certain bits from 0 to 1 or 1 to 0. And what we need to find after every query is the number of non-empty subsequences of S. Well, not the number, but the sum of all of their scores. So that is the problem. Here I will discuss until finding a good description of uh, the score, and then I will show how it can be simplified very much into a combinatorial expression. And after that, it should be very clear how we can handle the queries without any difficulty. Okay, so the first step to any counting problem is better understanding what we're trying to count or sum or whatever it is that we're really trying to do. Here we have this very weird expression called the score of v. So it is in our best interest to first characterize what that means. Um, so V is a sequence, of course, of zeros and ones. So let's perhaps take an example. Now, what is this strange quantity FVLR? That is telling us FVLR is simply, in fact, the length of the substring from L to R. That's R minus L plus 1. And we're subtracting from it 2 times the number of zeros present. So in some sense, the zeros are punished by -2 and the ones are simply rewarded by +1. Actually, everything is rewarded by +1. Yeah. So does anyone have any ideas on how we can better reinterpret this strange expression? Okay, so let's try to look at the contribution of each one and each zero to this sum. So a particular one, well, first of all, it adds +1 because it is counted in the length, and it contributes nothing here. So it's like -2 times 0, which is in fact 0. So every one contributes a +1 to this expression FVLR, given, of course, that this one lies in the interval L to R. Next, every 0, it contributes +1 from here and -2 times 1 from here, which is summing out to -1. So all we're really doing is assigning a value of +1 to all the ones and a value of -1 to all the zeros and adding up these +1s and -1s over our target interval LR. That is perhaps the best way to interpret FVLR. So all that really means now is we can just change all the zeros in our sequence to -1s. So let me do that. -1, 1, 0. Sorry, no zeros. -1, 1, 1, -1, -1, and 1. And all FVLR really means here is, let's say I pick L and R as this, is essentially the total sum. Here in this case, that's just 0. So now we've reduced FVLR to a nicer form, which is simply all about summing up two things. Now we are interested in maximizing the product of quantities like this. So now surely I hope many of you will see that there is a linear algorithm for computing the score by using this. So if we look at the sequence, we can simply compute all prefix sums and all suffix sums, and all the score really means is the maximum value of an expression of the form prefix of I times suffix of I plus 1. Of course, here by convention, we will assume prefix of 0 to be 0 and suffix of n plus 1 to be 0. I hope I'm clear so far. So now that we have a linear time algorithm for answering these um, queries for, let's say, the score of the binary string, we already have an exponential solution to the original problem. But given that we are also updating, and because n is very large, up to 2e5, that just already makes this a completely unviable approach. And therefore, we need to characterize better. We must find a better description for the score of a binary string. Now, we have prefix of I times suffix of I plus 1. And there is something very interesting about these two numbers. Can anyone tell me what that is? So I will give a hint. The description comes from looking at the total sequence and assuming that it has a total sum of, let's say, S.
One, if the prefix I is something x, then suffix I is s minus x.
Yes, excellent. So as Aman rightly noted, if we denote prefix I as x, then suffix I plus 1 is simply s minus x, because in fact 1 to I and I plus 1 to n partition the entire string into two pieces. And if this has some x, then this must have some s minus x. So this means that we are now simply trying to look at x times s minus x and trying to find the maximum value that this can take. So let us imagine for a moment now that x was not forced to be a prefix sum, and it could be any integer. Can anyone tell me what the maximum value that this expression takes as x varies over all integers?
S by 2.
Exactly. This um, function is a quadratic in x, and because it is of the form sx minus x squared, it has a negative leading coefficient for x squared, and therefore it's a parabola that faces downward, and thus it is maximized at the midpoint, which happens to be at roughly s by 2 because this is 0 and this is s. So if this were our 0 line, I'm assuming for now, of course, that s is at least 0. This is not necessary, but we shall assume this for now. Then the graph really looks like this, and it attains a maximum at s by 2. Well, not really s by 2 because s could be odd and then we don't have an integer like s by 2. But really, this happens when we choose x to be really close to s by 2, which is just floor of s by 2 times ceil of s by 2. Okay, so now we know that if x were allowed to be floor of s by 2, then that would be the best possible answer. And now we need to rely on a property, a very useful property of +1 -1 sequences, which is that their prefix sums are change very continuously. They change by at most 1, simply because we either add +1 or subtract -1. So using that, we know that if it took the value 0 at some point, which it does because prefix of 0 is equal to 0, and it also takes the value s at some point because prefix of n is equal to s, it follows that while we go from 0 to s, maybe it will have a very strange path, but it will take all the values between 0 and s, which means that prefix of I or x can be any value in the interval 0 to s or s to 0 depending on whether s is greater than or equal to 0 or at most 0. Now, because x can take all the values in this interval, it can in particular take s by 2 floor or s by 2 ceil. And what that tells us is that because even if x were allowed all integers, the best we could do was by choosing an integer like this. And since we can already choose an integer like this, it just tells us that the score of a sequence is nothing but s by 2 floor times ceil of s by 2 for s at least 0. For s less than 0, we can simply multiply all the elements of the sequence by -1, and it changes nothing because prefix of I gets multiplied with -1, and so does suffix of I plus 1. And so both of these change by -1, which makes the product remain the same. And so we might as well assume s at least 0 by replacing s with its absolute value. And now we know that the answer is simply this. Therefore, we have achieved the very surprising result that the score of any binary string only depends on the absolute difference of the number of zeros and ones between. Or in our +1 -1 terminology, it only depends on the sum of all the values. I hope I'm clear so far.
Could you give a like crude proof to this floor into cap value?
Um,
Why are we taking this particular value?
um, which part of this argument was not clear? So the argument is essentially that even if this were, so here I'm looking at quantities of the form x times s minus x, where x is prefix of I. And so x is obviously an integer. And so I can't hope to do better even if I were allowed all possible integral values for x. And from the graph of x times s minus x, we know that it's maximized around the midpoint. So that's at s by 2 floor. And so the maximum value that this could take, even if x were allowed all integers, would be this. So I can certainly not do better than this, but I can obtain this because floor of s by 2 lies between 0 and s, and therefore I can reach it. And so I can select x equal to floor s by 2. So that means there will be some I such that prefix of I is equal to floor s by 2. I may not know where it is, but I do know that it exists. And because that is true, that means I can obtain a score of this. And because I can't do better anyway, it tells me that this is the answer.
Oh, got it, got it.
Okay. So with this description, we are even closer to solving the problem. Now, this in fact can be reinterpreted as floor of s squared by 4. This can be done by just doing some casework. So let's just quickly do that. If s is equal to 2m, then this is just m times m, which is m squared. And so this formula holds true. If s is equal to 2m plus 1, then this is simply m times m plus 1 equal to m squared plus m, which is also just 4m squared plus 4m plus 1 by 4 floor. And so this formula holds true in all cases. And so we've achieved this very nice expression for the value of s squared by 4, sorry, for the score of a string in terms of the sum of its uh, elements. Okay, now we come to the next step, which is computing the sum of the score over all the subsequences. That's the next thing we need to characterize. So right now, we do understand the score of a string very well. What we don't understand is the sum of the score over all subsequences. Can anyone give me ideas on how we can start counting or simply calculating the sum of all the scores over all subsequences? So the important thing to note is that the score of a sequence only depends on the sum of all of its elements. In particular, it only depends on the number of ones and number of minus ones we choose. So if our original sequence, for example, had, let's say, m plus ones and n minus ones, I'm sorry for the conflicting notation. This n is already there. So we'll just assume that the sequence now has length m plus n, and there are m plus ones and n minus ones. So then when we sum over all subsequences, all we're really doing is choosing a particular number of plus ones and a particular number of minus ones. How many ones could I choose? Let's say I show that as a variable a. This could vary from 0 to m, and the number of minus ones I choose could vary from 0 to n. How many ways are there to select a subsequence such that it has exactly a zeros and exactly a plus ones and exactly b minus ones? Can anyone tell me that? So this, for example, is some string with m equal to 3 and n equal to 2. And let's say I want to select 1 plus 1 and 1 minus 1, a subsequence that has 1 plus 1 and 1 minus 1. How many ways are there to do that?
Does M choose A cross N choose B?
Exactly. There are m choose a ways to choose the a positions that will get us the plus ones, and n choose b ways to choose the positions that will get us the minus ones. And so it is indeed m choose a times n choose b. And over all of these choices, what score will we sum? Can we describe the score in terms of a and b?
M minus N. Sorry, A minus B. Right.
Yeah. So the sum of all of its elements is equal to a minus b, and that tells us the score is the expression we had proven earlier, a minus b whole squared divided by 4. So now it has become this. Now one could argue that maybe this is not the most pleasant form to look at, which is true, but now we have the opportunity to, we've sort of reduced it to a very algebraic form, and it's all about simply computing this and re-understanding this in a better way. So we'll do that now. The first thing that is sort of problematic is a minus b whole squared by 4. And no, not the expression itself, but rather this floor, because that leads to two possible choices and it's sort of problematic. So let's drop that for now. So for now, we will in fact ignore the floor. We will correct the error we get from doing this later on. So for now, let's say we just had to compute this sum. How could we go about that? Okay, so we'll start by expanding this out. It expands to a square minus 2ab plus b square divided by 4. Let's get rid of the by 4. It's not adding anything in terms of computing difficulty. We can simply divide by 4 at the end. So it's really this expression that we're dealing with. And so the sum just becomes sum of a to 0. Let's actually split this into three things based on this, this, and this. So all we really need to sum is this expression. Sorry. B equal to 0 to n, m choose a, n choose b, a squared, and I will in fact simply copy this and paste it three more times for the other expressions. This is with negative 2ab, which we can just take the negative 2 out there. We've got ab in here, and the final thing is with b squared. So that just makes this a b. So let's discuss how to sum each of these individually. Let's start with this one. Can anyone tell me a way to compute this? Okay, so one thing that we can do here is rely on the fact that m choose a and a square have nothing to do with b, which means that we can just send them out here. And so this becomes sum a to 0 to m choose a times a squared times sum, one second, sum b to 0 to n times m choose b. And we simply need to compute this. I'm sorry, but could you mute yourself? Uh, okay. And so we just need to compute this. And now the final thing is in observing again that this expression only depends on b and has nothing to do with a and m. And so we can separate even this. And so it just becomes the product of these two numbers. Does anyone recognize what this is?
2 to the power n.
Exactly, that's just 2 to the power n. And the other expression is this, which is sort of similar in the sense that we now simply have this weird a square in here. So let's also discuss how to calculate that. In general, if you have expressions of this kind, where you have m choose a times a function of a, maybe a squared, it could also be a standard way to do this is by using what are called generating functions. So we can write 1 plus x to the m as 1, sorry, m choose 0 plus m choose 1 times x to the 1 all the way till m choose m times x to the m. And evaluating this at 1 actually gets us the regular 2 to the power m. But now if we want to produce this sum, we need this extra a, and the way we do that is by differentiating. And the reason differentiating works so well is because it sends the 1 here, the m here, and so we can sort of extract that particular term that we need. So in particular, if we differentiate this, we get m times 1 plus x to the m minus 1, and this is equal to sorry, m choose I times I uh, times I times x to the I minus 1. And so in this, we can simply set x to equal 1. And that tells us that this sum is equal to m times 2 to the m minus 1. Can anyone tell me how we can get to a square? So the idea, in fact, is to multiply with x again to obtain mx times 1 plus x to m minus 1. And that gets us m choose I times x to the I. And now we can differentiate again and get this I outside, which will get us I squared, which is exactly what we want. So let's differentiate this quickly. This is simply m times m minus 1 times 1 plus x to the m minus 2 plus, and the other possibility is to only differentiate, right? And that's just, sorry, messed up, I believe. This should also have an x plus m times 1 plus x to the m minus 1. And this is equal to sum m choose I squared x to the I. And now finally what we can do is set x equal to 1 again to obtain for the very last time m times m minus 1 times 2 to the m minus 2 plus m times 2 to the m minus 1 equal to sum of m choose I squared. So just to write all the formulas that we've derived here, we have the standard m choose I sums to 2 to the m choose I times I sums to m times 2 to the m minus 1, sum of m choose I times I squared sums to that quantity over there, which is just m times m minus 1 times 2 to the m minus 2 plus m times 2 to the m minus 1. In fact, there is a combinatorial way to um, look at all of these. And so that would be simply to see this as I choose 1 and m choose 1. And here, if we look at m choose I times I choose 2, that's just I square minus I by 2. So that's like subtracting this off from here and dividing by 2. And that is simply going to get rid of this term, and we're going to be left with m choose 2 times 2 to the m minus 2. So we in fact do have more general results where this 2 can now change in all of these places, and we keep getting higher and higher degree formulas. But that is beyond the scope of what we discussed, what we're going to discuss today, so we can ignore that. Anyway, so the main idea is that we know how to compute all three of these sums.
Archit, if it won't take much time, could you just give some reference to what you just suggested for higher powers?
Um, so I will just write down the formula. I can't think of a reference for this, but it should not be very difficult to prove. So, okay, hold on just a second. This is 2 to the m 2 to the k. Okay, so here's a proof for this, a combinatorial proof for this sum, um, since you asked. So we're going to be seeing this as an interesting process where we have m elements. We're selecting, first of all, I of them, and then selecting k of them. So imagine that I was trying to count the number of ways in which I can color elements of this 1 all the way till m in three colors, let's say 0, 1, and 2, such that the number of elements that are 2 is equal to k. So there are two ways to count this. First is to fix the number of the places that I color 2. That can be done in m choose k ways. And then for each of the other m minus k leftover elements, I have two options to either assign them a 0 or to assign them a 1. The other way I could do this is by first deciding the set of zeros. Let's say that there are I m minus I zeros. So that takes m choose m minus I, which is just m choose I again. So this is the number of ways to select the zeros. And now I have the ones and twos, and I want to select exactly k twos. And so I choose k ways to select the twos, which will then also select the ones. And here I can vary everywhere from start to finish. And so this also gives us a combinatorial proof for this sum. In particular, this could be applied to k equal to 2 to establish this in an elementary way, avoiding things like generating functions and calculus. Okay, so now that we've
Thanks a lot.
yeah, so now that we've discussed that, let's return to what we were trying to compute. So we know this to be 2 times n, 2 to the n, and this, we know that expression, let's just call it f of m, f2 of m, if you will, and this is maybe f1 of n, f0 of n. So this is just that. What about this? Can anyone tell me if we can similarly separate this as well?
Yeah, m choose a into a can be part of the previous sigma and
Yes,
the other part.
excellent.
Yeah.
So we can separate in this way, where the negative 2, of course, stays on, and we select this and take them outside of this sum to obtain this product. And now these sums, you'll recognize that they are simply what we wrote over here. And so in fact, we know these as well. So we can express these as f1 of m and f1 of n. And this, well, some of you might have realized that we've already computed this before. So could you tell me what we'll write here? So this is simply the same sum as up here, but with mn interchanged. And so this is really just f0 of m times f2 of n. Okay, so what we've established with all of that effort is that the sum of a minus, let me just copy the sum from up there, and that will be significantly quicker. So what we've proven, uh, what we've proven is that this sum, let's add the by 4 now, is equal to 1 by 4 times, we first have f2 of n, f2 of m, f0 of n, minus 2 f1 of m, f1 of n, plus f0 of m, and f1 of n. And f0, f1, f2, as you all remember, are simply those functions that we defined up there. f0 is simply the regular 2 to the m. f1 is m times 2 to the m minus 1. And f2 is that silly expression that we derived earlier. Now, we know how to calculate this, therefore, without the floors. Why do I say we know how to calculate this? Because if you think about it, f0 of n can be computed in O of 1 time. The reason it can be computed in f1 time is because this is just a power of n, so the power of 2, and so we can just pre-compute all the powers of 2 up to the length of the sequence maybe, and we can compute this very quickly. f1 of n is just n multiplied with the power of 2, so that can also be done in O of 1. Similarly, f2 of n is also not anything very mysterious. If we simply go back and look there, all of this can already be pre-computed. This is just some numbers. This is just m. So we can already multiply these two. We already have these powers of 2, and so we can multiply with them as well, and then we just have to add. So overall, all of these functions can be computed quickly in constant time. And so these functions are as good as we could actually just write functions for them, f0 of n, f1 of n, f2 of n in our code, which would then just compute these. And without the floors, we have practically computed the sum, which means that this is essentially just the sum of score of all subsequences of our string, except for the floor part. So the only thing we're not accounting for is the floor. So let's try to rectify that. Can anyone tell me what this difference is? What's this equal to? So this is what we wanted to count, but we've counted a little over that. If you remember, the floor of a number is always small, at most the original number. And so we've sort of overcounted a bit. How much have we overcounted? What is this difference? So if a minus b is even, we've not overcounted at all because the floor of its square divided by 4 is just the number itself because the square is divisible by 4. And so in that case, this would be 0 if a minus b is even. But if a minus b is odd, and if you remember, earlier we had this as the actual value, whereas we wanted 4m squared plus 4m by 4 in the actual sum. And so we're overcounting by this 1 by 4, which makes sense because we should be overcounting by a non-integer because this is an integer, whereas this is not always an integer. And so this is 0 if a minus b is even and 1 by 4 if a minus b is odd. So now all we need to next compute is, if I define a function f again, let's say of a minus b this way, which is like 0 if it's even and 1 by 4 if it's odd, then all I need to compute is this. Now, a minus b is only going to be odd when a and b have opposite parity. And that's the only case we need to count for because in the other, the sum is not contributing anything. It's just 0, right? So we can consider first the case where a is even and b is odd and try to count this. So in that case, f a minus b is simply 1 by 4. And so we can just send 1 by 4 there. And it's as good as doing the following sum. Now, some of you may realize yet again that we can again split this. And we again obtain the following sum. Now, now we're interested in this very new quantity, which is we only want to sum over all the evens. Now, this can again be done with a small trick. Well, really, this can be done in simpler ways as well, but I will discuss the genetic functions idea nonetheless. So here we again have 1 plus x to the n as equal to um, 1 m choose I times x to the I, the sum of that. This time we're only interested in I if it's even. How do we do that? We need to obtain some sort of an alternating thing. And the way to do that is by replacing x with minus x. So if we instead look at 1 minus x to the n, that's m choose I times x to the I times minus 1 to the I. And this minus 1 to the I is going to be minus 1 when I is odd and 1 when I is even. So if we were to add these up, that would tell us, uh, that would give us a contribution if and only if I were even. So if we sort of add these up, let's say 1 plus x to the n plus 1 minus x to the n is just m choose I times x choose I. And when I is odd, this is actually having a coefficient of plus 1, well, plus 1 m choose I. And this has a coefficient of negative 1 or negative 1 m choose I, which sums to 0. And so in odd, this sum doesn't appear. So this is really just I even this, except we need to take care of something. We're counting plus 1 and plus 1 in both places in the even case, and so we just need to write a half here. Sorry, not a half, but 2 here. Now, to compute this sum, all we need to do is again set x equal to 1. So we get 2 to the n is equal to, that becomes 0 by the way, is equal to 2 to the n is equal to this sum I even m choose I and m to x. Yeah, just this. And so we can take off that 2 and this becomes 2 to the n minus 1, m minus 1. And so this tells us that this sum is actually just 2 to the m minus 1. What about odd? Well, odd is the same story. In fact, we don't need to repeat this argument again even, because we know that the total sum, odd and even included, is 2 to the n. And so if I remove the even stuff, which is known to be 2 to the n minus 1, the odd stuff is also 2 to the n minus 1. So this is also just 2 to the n minus 1 and 2 to the n minus 1. And then we also have a 1 by 4 over there. So that just tells us that this particular part of the sum is just 1 by 4 times this. Now there's also another case if A and B have opposite parity, and that is A odd and B even. Can anyone tell me what the answer in that case is? If A is odd and B is even? So obviously here odd and even did not change anything. And so it's in fact the same as this. And so that is also just 1 by 4 times this number. So all in all, this really becomes 1 by 2 times 2 to the m plus n minus 2, which is just 2 to the m plus n minus 3. So this is how much we overcounted by. And so our final answer is nothing, if I just add a floor here, it's just this minus 2 to the m plus n minus 3. So now if you notice, given m and n, I can compute this entire expression in O of 1 because each of these take O of 1 time to compute. And 2 to the m plus n minus 3 can also be pre-computed. And so all of this takes O of 1 time, which means that I can calculate this expression in O of 1 time. And so given m and n, I can do this in O of 1 time. Now, I think it should be very clear how we can handle updates of the form 0 changing to 1 or 1 changing to 0, because all they really do is change m by 1 or n by 1. So you either do m comma n goes to m minus 1 and n plus 1, or m plus 1 and n minus 1. And in either case, we can just recompute that completely and we can answer in O of 1 time by simply storing m and n. And of course, because all of this is linear, we've solved the problem in O of n plus q time, where n is the length of the string and q is the number of queries. Okay, so with that, this problem is done. I recommend you all solve this problem so that you understand all the arguments that were made. Um, yeah, I think that's it for this problem. Any questions? Okay, next we can move on to this next problem. I've sent the link in the chat. I'll just explain the statement as well once. So the problem says that we have a tree on n vertices. Let me just draw a tree here. And every single edge is a weight, W1, W2, something, something. And we're given an integer s as well, which is sort of an upper bound on each of these Wi. And what we want to count is the number of graphs that we can create on the same n vertices, such that, 1 second, I think, yeah. So this is from 0 to, no, it's from 1 to s. And we have to find the number of graphs where it's connected and it has only one spanning tree, and that spanning tree is the one you see here. So for example, essentially it's asking what sorts of new connections could I add such that everything is still fine. Again, the trees can be quite large. It could have length up to 2 times 10 to the 5. And S is also very large. S is up to 10 to the 9. And we need to solve for this. So let's again, so if you've noticed, there's sort of a pattern here to these problems, wherein first you need to interpret the condition in a way where you can start being mindless about things. So for example, here, the place where we really started being mindless is perhaps when we got to this expression. After that, it was just about computing that expression by using some algebraic techniques. But before then, this was the really difficult part of the problem, where we had to figure out what the score of a string is, where we had to argue for the score being s squared by 4th floor. So this part here is somewhat similar, and this part is all about what does it mean for a graph to have exactly one minimum spanning tree and it being equal to the one that's given here. Okay, so to do that, let's try to look at this one edge at a time. Imagine that we have a tree. Let me also assign it some arbitrary weights. And let's say I look at two vertices. So let me just mark those vertices. And let's say I'm potentially adding an edge between the two of these. What possible values could this edge weight have? Remember, the original tree must remain the minimum spanning tree. So could this edge, for example, have weight 1? What do you guys think?
Uh, no, because the current distance is 7 plus 3 plus 9. So any value greater than that, it should have, I think.
Okay. So could it be 8? So notice how all of the edges along the path from this one vertex 1 to vertex 2, if I cut any of them, it sort of breaks the graph into two parts. But I could remerge them potentially by using this edge. And so this edge must certainly be costlier than all the edges along this path. And therefore, if this has weights 9, 3, and 7, this must have weight at least 10. And so all we really need to do is now compute at least, we need to simply compute the number of ways we can select this edge's weight from 10 to the upper bound s. So one of the first steps we'll do is get rid of the possibility of there being no edge by simply treating no edges as edges with weight s plus 1, which is sort of a dummy infinity for us here. I hope that makes sense because all the weights are at most s, and so adding a weight of s plus 1 would never actually be used, and so it's as good as having no edges at all. And so we can simply increase s by 1 and assume that every single edge is drawn and given some weight. Now, for a given u and v, if max of u comma v, well, let's say p max represents the maximum weight of an edge from the path to u to v, then we know that we can choose anything greater than this and at most s. How many numbers are there between these two? Could anyone tell me that?
S minus P max plus 1. Right?
If it were actually closed on both ends, then it would indeed be plus 1. But since the maximum weight itself is disallowed because of the condition that there is a unique spanning tree, and here there would not be a unique minimum spanning tree because I could delete that common edge and introduce this one, and that's a new spanning tree with the same weight. And so, in fact, this plus 1 is not allowed, and this inequality is strict. And so we just have to get rid of this plus 1. And so the number of ways to do this for every edge is just this. And therefore, the answer is now product overall u comma v times s minus p max u comma v. And here I should remark that u comma v not edge. Of course, again, note that this s prime is different. It's in fact the original s plus 1 because we also needed to account for the case of there being no edge at all. Anyway, that's just a minor detail. Now all we need to do is compute this sum. Naively doing this takes n squared time because we need to go over all u comma v, pre-compute these uva values via a DFS, and then take this product over all pairs u comma v. So we need to do better than that. So here we're going to do the following. Let's say the weights are w1, w2, all the way till wn minus 1. We're going to order them. Let's assume that they're in increasing order this way. And the idea is that the Pmax from U to V can only be one of these values, obviously, because it has to be an edge. And so we could now try to count how many times it is the first edge. So let's say that over all the pairs of the graph that don't go over that edge, let's say there are U1 ways, actually, let's call that N1. Let's say there are n1 ways to choose a vertex u and a vertex v such that the maximum along the path from u to v is w1. Let's call that n1. Let's define n2 all the way till n minus 1 similarly. Then all we need to compute is s minus w1 to the power n1 because the same w1 appears n1 times. And this I could also just write it this way as multiplying this over all 1 to n minus 1. This can be found with binary exponentiation again in quick time. So all I really need to do is compute the ni, and then I'm done in linear time. So my job now is therefore only to compute these numbers. So now the counting part of the problem is perhaps gone, and all we really need to care about is this tree problem where we need to count the number of pairs of vertices that have a certain edge as the maximum weight at a certain given point of time. To do this, we're going to use a very common idea in these types of problems, which is a sort of a sweep line algorithm, where we're going to introduce edges in increasing order of weight. So let us start with the original graph being completely empty, and we introduce uh, vertices of a particular weight in order. So let's actually switch it up a bit. Now, instead of counting n1, which was the number of pairs u comma v with p max u comma v equaling w1, let's now relax this. So it's only about at most w1. So this is ni, where the number of u comma v with p max of u comma v at most wi is just ni. Now, all ni really means is if I look at the graph or the instant of the graph when only the first I edges were introduced. So I only had W1, W2, all the way till Wi at the time. Then U and V were connected. That is simply this new definition of n prime I. The number of U comma V such that P max of U comma V is equals Wi is simply the number of connected uh, pairs of numbers that were there at this point in time. Actually, I think it might be simpler to understand this, perhaps even without the use of ni prime. So maybe I will do that. Okay. So now we just need to compute this. So let us consider the moment in time where we introduced wi. So let's say wi connects the two of these, and these guys were already in their own components before this. Now, when we introduce wi, what does that tell us? We want this to be the maximum path along the maximum path along all the on the path from u to v for the vertices u and v, which tells us, and also all other uh, edges on the path must have weight at most wi as well. And so what that tells us is that we're just looking at some u over here and some v over here, and we just need to count the number of pairs of u comma v that we can select across these guys, except for this one singular edge. So all we're really doing is if this component has size C1 and C2, then the answer for our problem is simply C1 times C2 minus 1. Minus 1 because we cannot consider this edge again because it's forced to exist anyway. And now, as I'm sure many of you realize, this can be solved with the very standard algorithm of DSU, where we simply store these components and merge them in increasing order each time. And each time we merge, we simply look at the component sizes, multiply them, subtract 1, and set that as our value of ni. There are some interesting details here, which I won't go into, which is what happens when multiple wi are equal to each other. This requires special care, but it is not too difficult to figure out the details, so I will leave that to you. So if there are C1 ways, yeah, so as I already said, there will be C1 times C2 minus 1 ways to choose these pairs, and so we can compute all the n. And because DSU runs in um, O of n alpha n time, because that's the average complexity of the merge and union functions, this entire solution takes this time to do the, actually, my bad, does not take this long. We are sorting, we are sorting all the edges, and that already takes us n log n steps. And then after that, all the other operations are close to linear or practically linear. And so the time complexity of the algorithm is O of n log n, which will work. And that's the problem. Any questions? Okay. So I do believe we're short on time here because the lecture has already been quite long. So I will not discuss F1. I will only discuss the E. So let me just send the link and then we can talk about this problem. So I will explain this problem with the help of this very nice image that the contest author is attached. So what we're given is a permutation like this. So this is perhaps a permutation of length 5, which is 4, 2, 3, 1, 5. So uh, this is just P1 equal to P2 equal to all the way till P5 equal to. And all that we're doing is sort of, and sorry, I forgot to mention this, but some of um, the blocks are also colored. So each of these elements also has a color. So it's sort of, they're also assigned random colors. So for example, C1 is red, C2 is green. Of course, we encode them by numbers, but that's what that is. And all we now do is perform this strange operation where we simply let everything fall down in order to obtain this. Now we're interested in answering how many P comma C pairs could we have had such that performing this operation on them would have resulted in the same thing. So maybe a different initial seed pair, but the final same answer, or the final same picture in some sense. Let's think about this maybe one level at a time. Can anyone tell me something very stupid about the first level? The color sequence over here is simply C1, C2, all the way till Cn. And if you notice, it actually stays fixed. It cannot possibly move because, well, all of them are already occupying all the space. Now next, we focus on the immediate next column that we have. Here, there's actually, in the place where Ci was in fact equal to 1, a hole has been created because it would not have extended all the way till here. And so these two sort of collapse onto each other. So each time, in some sense, one element of the sequence dies out and the others merge. So now let's try to reverse it and try to count in how many ways we could have possibly reversed it. So let's say that we're looking at this. So we're only looking at, let me actually perhaps select that out just so that we're very clear. So let's take a look at this part. How many ways are there to actually unroll this into a sequence, a valid P comma C pair? So here there is only one way to do that. Because we are forced to send this up to make the colors match, and there's no other way to make the colors match. Where do we get free will? Let's also discuss that. For that, we have the other example where we have the following test case. Oh, there's already an image for this, where all of them have the same color. In this case, let's try to calculate the number of answers. So from this, how many ways are there to actually go back? Let's sort of think about it from here. Let's say that the number of ways so far has been n, and now we want to actually make it match up with this. How many ways are there to do that? So we need to look for ways to actually push things up. So we could decide to choose all of this to go up. And the only times when we can do that is when these colors match, etc. In particular, if we now think about destroying the original sequence one step at a time, all we're really doing is looking at the currently destroyed vertex, so that's here, and looking at its neighbors which are still present and counting how many of them are equal to its color as well. For example, in this sequence, it would be like deleting this one vertex, and looking at how many people in its um, neighborhood, let's call it, are also equal to the same color. And the answer here is in fact zero. Uh, and so, well, not technically zero, technically one, because we do need to account for that that one index being in its position as well. So there's exactly one green cell in this colors component, this cells component. And so we simply have one way to figure out where it goes. Next, we look at this vertex. This got deleted. That also has only one way because there's only so many things in this component. Then when we look at 3, that also has only one distinct thing in its component. And so that's also 1. And it's just 1 all the ways. And so that's just 1. Here, when we delete this, there are 2 people in the component. So we'll in fact multiply with 2 here. Sorry. There's not 2 people in the component. There's many more. There's in fact 5 people in the component because all of these are in the same component. And so we multiply with 5 here. Next, we're at this level. The smallest guy is 2. And so when we go here, sorry. The smallest is this. And so we look at all the components of this. And that's again just 4 because we need to count this and all 3 of these. Then when we go for 3, we've got this vertex and both of these. And they are also part of 3 components. So here we've got 3. Next, we're looking at this exiting because that's the smallest and this is 2. So that's into 2. And then finally, we've got this as 1. And so that just makes the answer for this a 120. So essentially, what it's become is looking at this sort of block. Let me find an example with perhaps a non-trivial answer. I don't think we've been provided with a test case like that. Let me just quickly find a non-trivial test. Okay. So we've got this test case. Let's just draw the diagram for it. So again, we need a 5 by 5 table. And this is the first thing. So the permutation is just 1, 3, 4, 5, 2. And the colors assigned here are just 3, 4, 4, 4, 1, 1, 1, 1, 3, 3, 3, 3, 3, and 3, 3, 3, 3. Sorry, only 2. So again, we're going to follow a similar logic. we're going to first look at the shortest thing, which is this one. I'm going to look at all the people equal to 3 in its component. So clearly there aren't any. It's the singular person in its component. So we have 1 times. Next, we're at this level. Next, we look at the next smallest component and we sort of blacklist this. This is no longer under consideration. This entire column is as good as missing. Now, sorry, this entire row is as good as missing. Next, we look at the next smallest, which is 2. So that's over here. How many people does 2 have in its component? This time the answer is not trivial. It has 2 people in its component, 2 and 5. And then we can just add 2 there and completely get rid of this. We can completely remove this. Again, just blacklist this. Next, we move on to 3. 3 is right here. This is our new shortest component. It has nothing other than itself, so that's just 1. So again, then we just get rid of it. Finally, we're left with the tallest people, which are 4 and 5. The shorter one is obviously 4, and it has nothing in its component other than itself. And so here it's again 1. And for 3 as well, we can see that it's again going to be 1. So in fact, the answer for this is 2. And this makes sense because essentially this 2 came from the 2 and 5 being equal. And that makes sense because this could have also totally been here and it would not have caused any problem. After performing the sorting, it would have resulted in the same final sequence. Whether the 3's are here or the 3's are there, it does not matter. And so by using that, we are able to count what's really going on. And now it all comes down to implementing this. The way to do that again is interestingly through a DSU. The way to do that is by realizing that if we initially treat everybody as a singular component, only combining people if their consecutive colors are equal. So maybe we're going to see 1, 2, 3 all the way till n. And we're only going to connect I with I plus 1 if they in fact share the same color, so they're in the same component. And now we're going to process these values in increasing order. So we're going to look at I, let's say, and the ith stage. And we know that at this point, everybody shorter than I has already been eliminated. And so we're only looking at people larger than I. What are the possible candidates for who can form components with I? That's going to be the immediate vertex to the right that is larger than I. So we're going to call that Ri. So let's say Ri is the immediate thing to the right, which is bigger than I. And then we similarly also have Li. If Ci has the same color as Cli, then that tells us we can merge these two. And if Ci is equal to Cri, then that tells us that we can merge these two. And after performing these merges, all we need to do is count the component size of this and multiply that with our answer. And we repeat this in sequential order for all 1 to n, and we'd be done. Now, this is very easy to do so long as we can compute Li and Ri in linear time. And we can do that in linear time as well, because this is just a standard task by using, say, the Cartesian tree, or um, also by simply writing a dp, let's say. This can also be done by using a segment tree and binary searching, but that is perhaps not the best way to do it, given that it can just be done very easily in linear time by using a Cartesian tree. And that solves the problem because, and the complexity is of course O of n, alpha of n, because we are doing a DSU on these guys and storing this. This can be optimized again further to O of n by realizing that our DSU here is very special in the sense that it's completely linear and that the only times we merge two things is if they're just next to each other. Using this, we can use even something like a doubly linked list to um, speed up things to linear time. But of course, that is not necessary. And so overall, that solves the problem in linear time, and we're done. Okay, I think we can stop for here today, and I'll take up any questions. Okay, then yeah.
Archit, could you share this whiteboard, please, in the Discord group?
Yes, sure, I can do
Okay, thanks.
that. Okay, so yeah, I think that this is done, and we can stop here.